In the last lecture, we discussed chapter number 9, which is life and evolution of stars. And today we're going to deal with the review questions. And these review questions will basically add information as well. And it's a kind of a review to what we did. Quickly, what we did in this chapter, we talked about binary stars, and we said binary stars is a system of 2 stars. And as you know, in our solar system, nothing is stationary. The planets are basically orbiting the sun, and the sun itself, it's rotating, and it's also moving inside the Milky Way galaxy. So the stars, when they move, which star is going to revolve around which star? And we thought that they find a common center of mass, and they revolve around the center of mass. And we talked about visual binaries, spectroscopic binaries, eclipsing binaries, and we said these are the techniques that we use in deciding the type of binary. That means it could be the same binary, but it's further away that we cannot see it visually. So we rely on one of these techniques. And then we talked about variable stars, and we said these stars that basically lost their hydrostatic equilibrium, so they start basically vibrating. So you have an inward pull from a gravity and out push from pressure, and that basically can cause at some point when the star becomes big, you may actually lose hydrostatic equilibrium, and we call these variable stars. And then we classified stars, we said spectral types of classification, and we said this is based on the surface temperature of the star, which is, oh boy, an F grade kills me. And from the spectrum, we can calculate the surface temperature of the star, and stars now are classified based on their surface temperature, and that's why we said the sun is a G star. And we said from the spectrum, we can also decide on the composition of what's available in the star, and we did that for the sun. And then we looked at HR diagram. And in the HR diagram, we said on the x-axis, the temperature increases this way, and in the y-axis, the luminosity increases that way. And if you go diagonally here, then the size will increase. And that also has an effect. We said the luminosity is proportional to the size, which is the radius, and the temperature. It's more affected by temperature. But when we talked about this, I told you have to pay attention to this color, red, yellow, and blue. So that's, and then we talked about the how stars basically generate energy. We said they generate energy in the same way as what we did in chapter number 8 through nuclear fusion. And then we talked about stars. They come into existence and they depart, and we divided them into 2 groups, stars that are less than 8 solar masses and stars that are more than 8 solar masses. And we said starting from giant molecular cloud, dense cores, and then a prototype, which is a T-Tauri, and then it becomes a star, and it starts an MS star or main sequence star and start basically functioning. Stars that are less than 8 solar masses, they die, and they may actually form what we discussed as a white dwarf. And those who are more than 8 solar masses, they can go all the way to become as a neutron star or a black hole. And we talked about, actually, it's a competition between gravity and the outward pressure. And we ended up with this slide here, where we said that stars that end up as white dwarf, and we said white dwarf basically have a size equal to the size of the Earth, and the mass is cannot exceed 1.4 solar masses, and we said this is known as the Chandrasekhar limit. And we said we may end up as a neutron star, like it comes to the size of a nucleus. So it becomes very small, like the size of a city, and it can go all the way up to 3 solar masses. And it may actually result in a black hole. And a black hole, basically, it's something that's very dense. So it will become very small. And that's in the event for very big stars. I'm just going to add something here, since we're not dealing with equations or anything, but for black holes, and in this chapter, chapter number 9, we only talked about what happens when a star dies. But when it comes to black holes, it's a subject on its own. There are the supermassive, the intermediate, the small ones. Even in the middle of our Milky Way galaxy, we have a massive black hole that has a mass 4 million times the mass of the Sun. And it has a radius 17 times the radius of the Sun. It's a huge in comparison, but it's also big mass. And sometimes you may hear they talk about the quasars, because these in the middle, they may actually emit radio electromagnetic waves and so on. So that's called the quasi-stellar radio sources, something like this. So you may hear things like that. And in the review questions, we'll talk about the spectral radius, and we say something about the event horizon. Since the black hole will become something very dense, okay? So the gravity there will be very strong, and there is something that we call the event horizon. And this is the point of no return. Once you enter, then that's it. You cannot escape from a black hole. This is actually, there is an equation for it, which we're not going to derive, but it's given as 2gm over c squared. C is the speed of light. M here is the mass of the black hole. And g is something that we call gravity constant, derived by Newton. Now, for the Sun, that's probably going to give you something like 2 kilometers in diameter. So imagine you condense all the Sun into a very small radius. It becomes very dense. And there is something that we call escape velocity. Now, if you want to throw anything up, it will always fall down because of the gravity of the Earth. So if you want to send a satellite, how will it escape the Earth and it doesn't fall back? So we always talk about this escape velocity. Now, when it comes to a black hole, we say that escape velocity is probably equal to the speed of light. So there is no escaping once you are in the event horizon, and it will become very dense. Just to mention a last point before I go into the review questions. Now, Newton said if there are 2 bodies and there is a distance r between them, he said the gravitational pull, it's equal to g m1 m2 over r squared. But he struggled with that. You look at the Earth and the Sun, and the average distance between the Earth and the Sun is 150 million kilometers. That's a huge distance. Yet instantly there is an effect, and he called that action at a distance. And we use this equation. Einstein basically said, no, what happens, what we call is curved space. So actually, if you have something like this and you put a mass, the space becomes curved. An object basically will follow this curvature here, and that's why they go in orbits and so on. In the case of a black hole, the black hole will become very dense. So it's kind of making very deep depression in the space. So anything that comes very close to it, the gravity will be very strong. But if you're further away, you may actually revolve around it. And many times you may hear people argue, so what happens if we come to the solar system and we take the sun and we put a black hole there with the mass of the sun? What will happen to the planets? Because most people always think that the black hole eats everything. Well, when you're further away, like what we have, the gravity will stay the same. So they said, well, probably nothing will happen. The planets will start orbit. But when you become very close to a black hole, and especially if you get in the event horizon, then that's it. So these are basically just a quick summary of what we did in the chapter. And today we're going to look at the review questions. And as I told you, you always look at these review questions as something that you try to understand. The first one, we know that giant stars are larger in diameter than the sun because, of course, this goes back to your HR diagram. They are more luminous, but about the same temperature. So if you recall what we did in the HR diagram, you will find that, for example, I think I have here. So when you look at the HR diagram, you go from lower temperature to higher temperature, and then the luminosity is here. Giants are usually here. So they're more luminous, but they have same temperature. Okay. That's why in this question here, we say they are more luminous, but about the same temperature. Now, giant stars are more luminous, larger diameter than the sun, cooler than the star, and you know the order, oh boy. So boy is very hot star, located above the main sequence in the HR diagram. All of these are basically fit the giants. They give us an HR diagram here, and they ask question, which star in the diagram above is most like the sun? So if you actually look at the main sequence, you will find out that HR 5337 is more like the sun. Which star in the diagram above has the largest, has the greatest surface temperature? Well, you look at the one that's in the O region, and the LNM basically is the one with the hottest surface temperature. Which of the stars in the diagram above has the largest radius? And remember, if you go that way, you increase in size. So Antares here is the one with the largest radius. 6, in an HR diagram, stars with the smallest radius are found of the diagram. They're found in the left lower corner. So you usually find them if you find them here, and that's series B, which is a white dwarf. 7, spectroscopic and eclipse duration observation of an eclipsing binary star can enable astronomers to calculate the mass and the sizes of the individual stars. Doppler shifts observation of spectroscopic binary stars can enable astronomers to calculate the masses of its individual stars. Binary, and you know binary means double, the stars can be detected by. And I told you, we have visual binaries, we have spectroscopic binaries, we have eclipsing binaries. So actually all of these here, options A to D, are used. Either see them as separate, or you see one star dimming the other, or you see absorption line to be appearing as one star. You know, when these absorption lines become one on top of other and then they move away. 10, the binary star Metz array is shown with the motion of members around one another. the mass of the visual binary pair of stars can be obtained from the time and the size of the orbit. So that's how we can determine the mass. 11, we know that the white dwarf Sirius B has a mass comparable to the Sun, because now we cannot tell its mass, but because if it is as in a binary system, and since we can decide the orbital motion and then we decide on the period and so on, we can decide on the mass because it is part of a binary star system with Sirius A. In the HR diagram, 90% of all stars are on the main sequence. The most common stars are lower main sequence. Remember, if you look at the HR diagram, they're mostly populated on the lower part of the main sequence. In the list below, the least common stars are, okay, so you have upper main sequence stars, white dwarf lower, so this is actually the upper main sequence stars are least common. If two stars are emitting the same amount of light, the star that is further will appear dimmer, and that's basically logical here. How can we tell that some stars are relatively close to us in the sky? Now, when stars are far away, you cannot detect their variation, but we say some stars appear to move periodically back and forth against the background of stars because of the Earth movement around the Sun. You know that the Earth is revolving around the Sun, and that may actually allow us to see the stars moving back and forth a little bit. That's when they are very close to us. But if they're further away, we're not going to notice that. Stars in the upper right part of the Hertzsprung-Russell diagram are always larger, giants and supergiants, when compared to stars near the middle of the diagram. In this question here, it's about Doppler shift. Just to remind you of what Doppler shift would do. You are standing near a railway track, and a train is moving toward you at 60 miles per hour and blowing its horn. What will you notice as the train moves past you? I told you about the Doppler shift. When things are approaching you, the wavelength shifts toward shorter wavelength, and the frequency will be higher. And the sound will get louder in the case of sound. And when they're moving away from you, the wavelength will shift toward longer wavelengths, lower frequency, and of course, it will be lower. So as the train approaches, the horn will sound higher in pitch than when it's moving away. And you know that's because when it's approaching, wavelengths are shifting toward lower wavelengths. We call it the blue shift in the case of light, and red shift when they're moving away, and that of course affects the frequency, and the frequency will affect the pitch. They give us a table here, and this table here, they give you a star name, and then they give you spectral type. And they ask question here in regard to this table here. The table below lists spectral types for each of 5 stars. Which star in this table would have the lowest temperature? So now you know the O, boy, and F grade kills me. So you look, you find that the O set is an M star, so that's the star with the lowest surface temperature. In 20, they asked the star with the highest temperature. You look, you have an O here, so Zeta or Zeta Per, it's the star that basically has the hottest temperature. What is the order of star colors with increasing temperature? Red, yellow, and blue. Remember when I showed you that in the HR diagram? Doppler effect states that the motion of any object can shift the wavelength of spectral light. And I told you they may go toward shorter wavelengths if they're approaching, and we call that blue shift, and they may shift to higher wavelength when they move away, and we said this is red shift. Which of the following stars is the hottest based on spectral classification alone? Oh boy, and F grade tells me. So the B here. In interstellar gas clouds may collapse to form stars if they encounter a shock wave. When they encounter that, they can move, gravity will take over, and that, of course, gravity will bring things in, and once the gravity brings in, that's when you have a chance of forming what? Forming a star. The HR diagram to the right, the line indicates the location of the main sequence. Which of the 5 labeled locations on the HR diagram indicates a luminosity and temperature similar to that of a T-Tauri star? A T-Tauri star is a little bit above the main sequence, and then it will become more in equilibrium, and it becomes a main sequence. So the location 4 here can give me something similar to a T-Tauri. The free fall contraction of a molecular cloud, you have a cloud, and a free fall here, it's basically like a gravity. So that's what we call a gravitational energy or potential energy. Can be initiated by a shock waves from a supernova. 27, proton chain needs high temperature because the proton must overcome the Coulomb barrier, which is the electrostatic repulsion between the positive protons. And we talked about that in chapter 8 as well, and we needed a temperature more than 10 million degrees in that case. The CNO, carbon, nitrogen, oxygen cycle, is the thermonuclear fusion of hydrogen to form helium operating in the cores of massive stars on the main sequence. That's the name that's given for this process here, when it's basically fusing hydrogen to helium, especially for the massive stars. We call it carbon, nitrogen, oxygen, CNO. If the sun produces energy by proton-proton chain, then the center of the sun must have a temperature of at least 10 million degrees, which is 10 raised to the 7. 1 million has 6 0, you 10, so it has 7 zeros, so it's 10 to the 7 Kelvin. The carbon, nitrogen, oxygen cycle, which is the CNO, combines 4 hydrogen nuclei to form 1 helium nucleus, which produces energy. That's the name given for this process. Okay. As I told you in one previous question, the region of the sun just below the photosphere transporting energy by convection. We already dealt with that in chapter number 8. The central cores of massive main sequence stars transmit energy outward by convection. Always, when you get near the surface, it's done by convection. While in the main sequence, a star's primary energy source comes from nuclear fusion. And I don't want you to confuse that with fission. Okay, we're doing fusion inside stars. And I told you that basically the future of nuclear energy. They building fusion reactors now. The biggest one is in France. I think in England now there is on the way of constructing one. China, I think, is making good progress, but in the future you'll hear that a lot. And if you have money to invest, probably it's a good idea to invest in nuclear fusion. Not all your money, but you can try investing some. I think there will be good return there. 34, as a star begins to form, the initial energy source is from gravitational potential energy. So while the star is in the main sequence, it's producing energy by nuclear fusion. But while the star is forming, it's coming because of gravity. And that's why gravity is, that's why we call it the gravitational potential energy. That's the initial start. 35, the lowest mass star cannot become giants because they cannot heat their centers hot enough. There are stars which are basically have very low mass, so they cannot heat their centers enough to have high temperatures for the nuclear fusion to take place. Planetary nebula is the expelled outer envelope of a medium star. And I told you, planetary here is a long name for the nebula. It's basically, you know, when you have a star becomes big, gravity is pulling inward, the nuclear fusion producing energy is pushing outward, but at some point, the gravity wins, and of course, the star will collapse, and you have an outer shell envelope that goes around. And we call that, for some stars, planetary nebula. It's not because of planet, but we're stuck with this name. The Chandrasekhar limit tells us that not all stars will end up as white dwarfs, because in the question after that, the Chandrasekhar limit is 1.4 solar masses. That's the limit. So bigger stars will actually go into something else. Okay, they may form a neutron star or a black hole. The energy a white dwarf emits into space is not replaced. A white dwarf is basically the material that's condensed into a size like a planet Earth. That's it. It doesn't do any nuclear fusion, but it's basically going to start emitting energy, and this energy is not replaced anymore. 40, a type 1 supernova is believed to occur when a white dwarf exceeds the Chandrasekhar limit, and this is also known as nova, but it's classified also as type 1 supernova when a white dwarf helps a big star in ending its life. Again, a nova is almost always associated with a white dwarf in a closed binary system, which is also a type 1 supernova. 42, as material leaves an expanding star and begins to fall into a white dwarf, an accretion disk will form around the white dwarf. And of course, when it exceeds the 1.4 solar masses, then that's when you have the nova or type 1 supernova. In 1054 AD, Chinese astronomers observed the appearance of a new star, something very bright, whose location now is occupied by a supernova remnant. It was basically something that's getting very bright because the star was going through an explosion. And I told you, things always happen in the past, but you wait till you receive the light. If we're lucky enough in our lifetimes, we may observe something like that. 44, massive stars cannot generate energy through iron fusion because iron is the most tightly bound of all nuclei. It's not easy to fuse anymore. You can, but it's very hard. So inside stars, you can produce all the way up to iron. Now, elements higher than iron are produced in the after supernova. You have regions that are hot enough, then you can produce the elements. And by the way, all the elements that you have in your body, they were once produced inside stars. Stars between 0.4 solar mass, remember about the M, and you see a subscript here with a circle and a dot in it. I told you that always means the sun because we use this as a reference in astronomy. And 4 solar masses, they undergo thermal nuclear fusion of hydrogen and helium, but they never get hot enough to ignite carbon. Like our sun, I told you, after when they start getting to iron, they get to the stage where we call it red giant, and then it's going to end its life, and it will end up as a white dwarf. For a star of sun-like mass, what is the last stage of nuclear fusion? Helium to carbon, and carbon, of course, trying to go to oxygen, but that's when it's going to stop. That's the last stage. The first stage is hydrogen to helium. But when it tries to go to carbon, that's when basically the star is nearing its end. What are the two longest stages in the lifetime of one solar mass? Well, it stays 90% of its lifespan on the main sequence. So it's an endless star, and then it dies and it makes a white dwarf, and white dwarf will continuously loses energy. So these are the two longest stages in the lifetime. Of course, they go through giant molecular cloud, shock wave, gravity in, and then they go in prototype star, which is a T-Tauri, then becomes a star, main sequence, and then giant, then after giant, they give us white dwarf. 48, what mechanism does an isolated white dwarf use to generate energy? White dwarfs do not generate energy. They only lose energy. 49, stars that have ejected planetary nebula eventually become white dwarfs. So the name here, it's basically planetary nebula. It's for the stars that eject white dwarfs. After what evolutionary stage does a star become a white dwarf giant? Where are elements heavier than iron primarily produced? Supernovae. That's in that region. Okay, you have region where you have very high temperatures and pressures and densities, and probably you will make elements that are higher than iron. 52, the explosion of a supernova typically leaves behind a shell of hot expanding gas with a pulsar at the center. That's a neutron star now. Or we can go to the other stage where it could be black hole, but that's basically you need bigger stars. The density of a neutron star is about the same as an atomic nucleus. I told you, you have an atom, a nucleus which has protons and neutrons, and then you have a cloud of electrons around. I told you the size of the nucleus is about 10 raised to the power minus 15. And the atom is about 10 raised to the power minus 5. So by ratio is about 100,000 times. So if the electrons and the protons combine, if the electron and the protons combine and they give you a neutron, so you're basically reducing everything to the size of the nucleus of the atom. A neutron star is expected to spin very rapidly because they conserve angular momentum when they collapse. And today I was teaching my physics, general physics 1 student about angular momentum and how things will become faster when you change something that we call the moment of inertia. And this is something when you look at the skaters, when they bring their body in, they start spinning very fast. So when something is spinning and then it reduces its size, it will spin very fast. And this is something in physics that we call conservation of angular momentum. So that's why here in neutron stars, we expect them to spin very fast because to conserve the angular momentum. 55, although neutron stars are very hot, they are not easy to locate because they have very small surface area. So you cannot see them visually. At extremely high densities and temperatures, electrons can be forced to fuse with the protons. The reaction produces neutrons. And that's what I told you when you get to neutron star. And of course, there is also elementary particles called neutrinos in the process. And we talked about neutrinos in chapter number 8 when we talked about fusion of in the sun. The density of is greater than the density of, and they give you options here. Now, black holes will be more dense than neutron stars or a pulsar, and a pulsar will be denser than a white dwarf. So here the right answer is a pulsar is greater in density than a white dwarf. A pulsar requires that a neutron star rotate rapidly, have a size of at least 10 kilometer, have a strong magnetic field, rotate on an axis that is different from the axis of the magnetic field. Well, 1, 3, and 4. And we talked about that when I was discussing neutron stars. I told you it has an axis about which it spins, and the magnetic field is not on the same axis. And that's why you can basically get pulses. So these questions dealt with the neutron star. Now, when we come to a black hole, there is something that we call the event horizon. And I think I told you here, when you get to the event horizon, it's like the black hole will have a radius, which we call here RS. This is where the event horizon, once you enter that region, that's it. Okay. It is the point of no return. That's what we call the event horizon, and it's calculated from here. So this is basically the and it's equal something that we call the Schwarzschild radius. Now, from that formula, we're not going to do the calculation, but just to give you an idea, if you use 2 solar masses and you condense them into a black hole, they will have a radius of about 6 kilometers. That means the diameter will be about 12 kilometers. So imagine you take something twice the mass of the sun and you put it into something like probably the size of small town. It will be very dense, and that's why black holes, they will have very strong gravity close to them, because in accordance with Einstein, mass basically curves space, and when you have something very dense, it will curve space very strongly around itself. And usually they say if you get closer to a black hole, that means in the event horizon, you will become spaghetti, because of the gravity is very strong. 61, an isolated black hole in space would be difficult to detect. Well, we will not know of its existence because very little matter will be falling into it. We need to see the black hole at action in order to see its effect. And I told you, I think in the beginning of the lecture, some argue that if you take the sun and you replace it with a black hole with the same mass, they said, well, the planet far away, nothing will happen. They will continue orbiting. But if they get closer, oh, they will be shredded. 62, the search of a black hole. Usually, when we try to look for a black hole, we have to look for a black hole in action. That means it's shredding material, and the material will be accreted, and there will be accretion disk. Now, not in the event horizon, beyond that. And that material will be moving very fast. So the energies that it will emit, it will be in the X-ray range. So we usually, remember what I told you that a white dwarf has to be in the size of 1.4 solar mass, neutron star up to 3 solar masses, and then you go. So usually here, it's when the mass of the companion is an axis of 3 solar masses, and the black hole is basically shredding that, you can see X-rays. Of course, there are other energies as well, but it's usually the X-rays. It tells us that material is moving very fast and emitting this energy. the material that accretes onto a neutron star or a black hole, a neutron star also, if anything comes close to it, because it's denser, it will have a greater gravity as well. It will basically shred the material, and the material that accretes there, it will be moving very fast, that it will radiate strongly in the X-ray. And remember, in chapter number 5, we talked about the electromagnetic waves, and we talked about that the energy is equal to hf, where f is the frequency. So X-rays will have higher frequencies, and I told you that basically you have something that is in the order of probably hundreds of thousands of degrees. 64, as material falls into a black hole, the material will experience time dilation, and the material will become hotter. Well, time dilation here, it's something that comes from Einstein theory of general relativity. It's when you approach the highest speed that we have in our universe is the speed of light. So I'll just try to, if you are in a car and there is a car ahead of you, now if you and the car ahead of you are going at the same speed, you will notice, you're not going to notice a difference. But if the car ahead of you is moving at higher speed, then you're only looking at that difference. So if the ahead of you is 140 and you're 120, relative to you, you'll say the car in front of you is moving at 20. And you can also add, in the case if you're going in different directions. But if I'm measuring speed of light is going to stay the same. It's not going to make any difference. So the only thing that's going to change is time. So when you approach the speed of light, time will slow down. And that's what we call time dilation. And I think there is a paradox by Einstein. Twins, when a twin stays here, the other twin goes into outer space in something that closer to the speed of light and comes back. When he comes back, his twin brother is an old guy and he's still youthful. And probably you saw the movie Interstellar, where actually the father is younger than his daughter when he came back. And that's also a possibility. You could be younger than your children or grandchildren if you basically go far away at speeds close to the speed of light. So in your frame, time will be slower. So that's what time dilation is. A black hole can be thought of as a massive body of infinitely small size. Infinitely mean here we're talking about compared to objects like the sun and so on. So we're talking about, let's say you reduce something to the size of kilometer as when you have something in very huge. Okay. So it becomes very dense, and that of course is going to curve space strongly around it, and it will have very strong gravity. The singularity of a black hole is located at the center of the event horizon. A singularity here is like a vertex. You know, when you if you wash your face in a sink and there's lots of water and then it drains, you will see it basically draining to the drain, and it moves like a vertex. That's a singularity. So the singularity of black hole is basically at the center of the event horizon. Finally, the escape velocity at the event horizon around the black hole is equal to the speed of light. That means if you get to a black hole, there is no escaping. There are now some arguments, but this is basically, there are some people, they say you can have what's called a warp space, and you can go from one universe to the next through a black hole and things like that. And you may actually hear stories about Alice going through a black hole. but gravity will be very strong, and they may study that you may go through to become spaghetti because the gravity will be very strong, so you become very thin, which is a good way of losing weight. But that's the likely event if something comes close to a black hole. Now, we only discussed the black holes here as an event when stars die. But I told you now, there are massive or supermassive black holes. Like even in the center of our own Milky Way galaxy, we have a black hole that has 4 million times the mass of the sun. And of course, around it, you will have lots of emission. And that's why sometimes they say quasars and so on. And other, remember we talked about the M87, where I told you they got a direct image of that. So you always look at something. These are not small black holes. These are massive black holes. And in the same line of argument that we say here, just to give you an idea, if we want to look at the Schwarzschild radius and how we calculate that, if we take the Earth, and the Earth is, I think the mass of the Earth is about 26, I think, times 10 to the 24 kilograms, something huge. And you make it a black hole, the radius of this black hole will be about 8 millimeters. So the diameter will be about 1.6 centimeters. It's like a marble. So if you can reduce our Earth, our planet Earth, into a black hole, it will be like a marble. And of course, in that case, if I told you about the, when we talked about the gravitational law, this R here will become very small. So the force of gravity will become very huge. And that's why I told you, when you get to a black hole, you will basically become like spaghetti. So with this, we cap chapter number 9. Again, I always tell you that these review questions, the purpose here, it's like a discussion, okay, and learning of ways that how I am going to test you. Of course, I'm going to challenge you with some questions where I test your knowledge of the material. Is this clear? Any questions on these? Any questions? Is this clear? Good. You got all of that.